This is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I am dealing with the course Computational Aerodynamics. And today's topic we will see the combined convection and diffusion formulation using finite volume method. Okay, so in the previous session, we have seen in depth about only the convection term. So in depth about the diffusion term, where we have discussed the aspect about d by dx of gamma d phi by dx. Okay, so if we take only the diffusion term, so what are the finite volume equations, and then how do we arrange the matrix with a sample example problem we have seen. To recap, so we have given some sign convention, so where P is nothing but a point of interest, so W is nothing but the node which is present on the left, which is west node. So this is the immediate left, which is west node. Then after we have E, which is called east node, which is right. Next we have the another east node EE, so which is immediate right. Right. The distance between this point P and the west node, you can see this one as delta x PW. Fine. Next, the distance between this P and E, east node, which is delta x P capital PE, and the distance between the point P and the face. So this is called the face. Fine. So since we are doing the finite volume analysis, and we are actually seeing the flux through the phases, so we are very much interested to calculate these values at the phases actually. So fine. So that's why we have taken the distance between point P and this phase W, so which is given as delta xp small w. Fine. Next is similarly we have phase E small e, which is the distance between point P and this one is delta xp small e. Fine. So this is what we have. So here for the sign convention, like whatever we have seen, it is for 1D. So if we go for 2D, so what happens? So you have point above which is called north and point below which is called south. So you have north and south, west and east. Fine. This is for 2D. For 3D, what do we have? So we have another which is called front, or let's say you have back. So you can take in this way. So when we have 1D element, so we have only west and east node. When we have 2D element, you have west, east, north, south nodes. When we have 3D element, we have back and front. Fine. So this is what we have seen for single source term. So here you can see the right hand side. So the source term which we had already, the diffusion term which we had already seen in the previous sessions. Okay. So what we have done? We have done the surface integral. So here you can see. So when we do the surface integral of d by dx of gamma into d phi by dx, so we obtain this equation. Fine. So since we are calculating the surface integral, so we need to evaluate the value of gamma and the a, and next phi at the surfaces actually. So this is what we need to do. Fine. So now additionally what we have, so we have, this is called the flux term or the convection term, you can. So as I told you in the previous sessions, so when you take a momentum equation, so on the left hand side you have the flux or the convection term, on the right hand side you have the diffusion term. So here the left hand side, this is called convection, the right hand side is called diffusion. So this is coming from the contribution of viscous, okay, and this is coming contribution of inertia. If you take the ratio of the left and right, so L by R, so this gives us Reynolds number. When we non-dimensionalize the momentum equation, so we get one non-dimensional reference parameter, so which is called Reynolds number RE. RE is nothing but the ratio of inertial force to the viscous force. Fine. So left hand side you can see that so rho u phi, rho u phi. So this is at the phase E, so which is here. This is at phase W, which is here. Fine. So phase E minus phase W. Fine. So what happens? So rho into U, this gives us flux, and rho into U, this gives us flux. The flux at the east side and flux at the west side. So the difference between the flux. Similarly, on the right hand side, you can see this is the diffusion term on the right side, which is E, and diffusion term at the left side, which is W. Fine. Now you can see we are taking some symbols, or let's say some notations, where so Fc is nothing but the convective flux, which is given as rho into U. Fine. So the diffusive flux Fd is nothing but gamma divided by delta x. So we are making this such a way that it is giving a short form. Fine. So to get the short form, like we are taking this as Fc, which is convective flux rho into U, and Fd, which is diffusive flux, which is gamma divided by delta x. Fine. So Fc into A into phi of E minus Fc into A into phi of W. So basically this is what we have. Fine. So the east flux minus the west flux. So this is called the east flux and this is called the west flux. So what is Fc? So this is called rho into U, which is convective flux. Okay. Now on the right hand side, so we have Fd. So what we are doing? So we are replacing this rho U as Fc and this gamma by delta x, okay, as Fd. That is the difference. So Fd is nothing but what gamma divided by delta x. So here we go. So this is at the east side and this one you can see at the west side. Fine. So since we are taking 1D element, so for the 1D element, if you take any cross section, so you take all the cross section, what happens? The area is same. Okay. So area at the east face, area at the west face is sample area A. Okay. So east face area, west face area, you take any cross section area, so that will be same for the 1D element. So, and as I told you, so there are different types. We have 1D, we have quasi 1D, we have 2D actually. So let's say 3D, 2D. So difference between 1D and quasi 1D is, so for the 1D, so the area is constant with respect to space, and the values of pressure, temperature, density, velocity, they vary with respect to only one direction, whereas area is constant. Now in the terms of quasi 1D, what happens? The area changes along the direction. So what happens? Pressure, temperature, density, velocity, they vary along one direction, but additionally you have the area changes along the direction. Fine, that is for quasi 1D. So here we are taking only 1D. So since it is not quasi 1D, so we have taken area as same. So what happens? So from this equation, so the A will be getting common here. From this A will be getting common. We can cancel. So therefore what happens? You can see here we have F convective flux at east face into phi of E. So what is phi actually? Phi can be taken as any flow variable. So phi can be so density, pressure, temperature, velocity. So any variable you can take, any flow variable. Fine. So convective flux at the east face into the variable minus convective flux at the west face into the variable is equal to, what do we have? Diffusive flux F of dE into phi of E minus phi of P. Fine. So phi of E minus phi of P, in the sense what do we have? So same here, phi of E is nothing but the value of flow variable at this point E. The value of variable at this point, sorry, P. So similarly you have phi of P minus phi of W. So W is this one. Fine. So on the left side we have the convective term, the right side we have the diffusion term. Fine. Now, so what do we have? So basically, even though we do the finite volume formulation, so we have the values at the grid points. Okay, so the major task is how do we get the values at these phases, west phase and east phase? How do we get actually? That is important. So what is the criteria? Like how we are supposed to get the values at west and east phase? So that is one. Now the one small technique is the interpolation or taking the average. So when you take, if you want to get the value at the west phase, let's say phi of small w is equal to phi of capital W plus phi of capital P by 2. So this is one formulation which we have. Fine. So if you want to get the value of W, or let's say if you want to know the value at the west phase, here what we are doing, so we are taking this value, we are taking this value, we are doing average of these two. Fine. Next, so if you want to get to know what is the value at east phase, we are taking this value, we are taking this value by 2. Fine. So this is what we have. So by doing this, so we will get what is small e, small w. Why? Because on the right hand side you can see already we have capital phi e, capital P. So since they are known values, there is nothing to be done extra. But here on the left hand side we have phi e, small e, and phi small w. Fine. So this is what we have. So you can see phi of small e, which is nothing but phi p plus phi e divided by 2, and phi of small w is phi p plus phi w by 2. So this is what we have, interpolate. Now if we have, let's say, the unequal distance. So since in this diagram you can see that the distance between these points, so let's say this is some equidistance, or let's say we are doing average. So if point is somewhere here W, we will take weighted average. Fine. So if we have it equidistant, we are doing average by 2, the simple formula. But if it is present at other place, so then this formula is invalid. If it is not equidistant, then we will be actually taking the weighted averages, right? So when we substitute these values, phi p plus phi e by 2 and phi p plus phi w by 2 in this equation, so instead of phi e, so what is this? This is total phi of small e. This is of total phi of small w. This is phi of small e, phi of small w, which is equal to phi of capital A, phi of capital P minus, so we have capital P minus capital A. So when we when we have got these things, so we will actually rearrange how this total, let us, you can take it as AP, the coefficient. So phi p, so we are collecting all phi p terms one side. Next we are collecting all phi w terms one side. Next we are collecting all phi e terms one side. Okay, so here we are rearranging the equation such that you are collecting all the coefficients of phi p and all the coefficients of phi w and all the coefficients of phi e. Okay, so again further, let's say if you further rearrange this phi p thing, you can see this. This is what FDW. So diffusive flux at the west phase plus convective flux at the west phase by 2. Next, diffusive flux at the east phase, convective flux at the east phase by 2 plus FC minus FW. So when we rearrange, so we get this one. So this one you can take it as AW. This one you can take it as AE. So this one you can take some A. Okay. So when we rearrange, so what we are getting? So we we got, so in the form of AP phi p is equal to AE phi plus AW phi W in this form. Let's say we got in this form. So that's why we are doing. Now you can see, so weighted average method. Now, previously we have done, let's say, only the average. Let's say you have this point and this point. So when we know this one, so since we assume that this is in between of these two, average of W and P we are doing. Now, so when we do the weighted average, when we do interpolation, so you can see phi of W can be written as alpha 1 phi W plus alpha 2 phi P plus alpha 3 phi W. So we will take all these three considerations. Fine, for the three nodes. So similarly, so if you have, let's say, the wind coming from this way, so UW is greater than 0. You have wind coming in this way, UE is greater than 0. Okay. So basically, by doing some mathematical operations, we will evaluate these coefficients alpha 1, alpha 2 and alpha 6 1. Fine. So with this, we have seen basically the combined diffusion and convection finite volume formulation, and we have rearranged in the form of AP phi P is equal to AE phi E and AW phi W. So the thing that is difference is when we take only diffusion and source term, here we have additionally convection term, and in the coefficients we have the convective flux, we have diffusive flux. So with this, the realistic approach for the fluid flow phenomena is possible, but since we are dealing with only 1D, so you can see only that one. So in the next session, we see for 2D, 3D how the equation changes. And additionally, we have seen for the weighted average between the point P and west node and point P and east node. So how do we do the weighted average? So if we take 3 points, we have done the quadratic interpolation. So on we will do. In the next session, we will see how do we do for the convection and diffusion flux. Finite volume method for 2D, 3D will be seen. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.